Our next speaker is Professor Rainer Blatt.
So, good morning, everybody. First of all, I would like to thank the organizers for organizing such a wonderful meeting. And I would like to express my pleasure to be here. It's an honor to talk on this symposium, Dan. And I would like to dedicate that talk to you by just saying, I would like to talk today about what I learned from Dan Kleppner. And the talk is about cavity QED, and we've heard that before, a passion for precision, but in my case it's also a passion for atoms and precision. And it's more a passion for single atoms, as you'll see a single atom right here, and there's a lurking mirror in the background. We'll learn more about that in a little while. So this is the menu of that talk for the next 25 minutes. I would like to talk a little bit about Dan Kleppner's idea about inhibiting spontaneous emission, and then just show you what I call the simplest interferometer that exists: one atom, one photon, and one mirror, or what's rather called a half cavity. I'd like to show you some absorption cavity effects with single trapped ions, and then delve into a few applications, how we achieve atom-atom entanglement using these techniques, and atom-photon entanglement using cavity, and finally, if there's time enough, to show you how we do quantum state mapping applications for quantum information processing. All of this happens at the University of Innsbruck, and of course jointly together the Academy of Sciences Institute of Quantum Optics and Quantum Information. So let's get started with a few things what I've learned from Dan Kleppner. I was always impressed to see these numbers very early on in 1963, and I tried to repeat some of these measurements with a few trapped ions during my PhD thesis, my diploma work, and later on we carried out more measurements than that. So this is where my passion for precision came from. I won't have the time to talk about these things today. But then there's also something that really impressed me very early on from Dan Kleppner. That was his paper, his famous paper about inhibited spontaneous emission, as early as 1981, and then we've seen a number of nice experiments by Randy Ulitus and the Jordans, and later on by the Harosh group and many others. But the question was always, can we see this with single atoms? Can we just probe the fields that there are there? Then we really just have boundary conditions just to change the mode densities. And here is what Dan Kleppner says. Any scheme for suppressing spontaneous emission is potentially useful to the art of precision measurements. There may be perturbations, but later on he says, in any case, the observations of inhibited or enhanced spontaneous emission would provide an interesting bridge between atomic physics and macroscopic electrodynamics. And I think this is really, it's a foresight that's incredible. And we nowadays use this, of course, as one of the bridges between, say, a stationary and a flying qubit as the interface function right here. That is the realm of cavity QED, which provides the interface between the stationary and flying qubits. And this is what's going to be the technique for interconnecting quantum information processors. Let me show you some of these experiments and where this comes from. Here's again the picture that we had before. This is a single trap barium ion, which is a 3-level system. You see the nice red and green laser beams. Now, here is a mirror lurking in the background, and this is a faraway mirror. Faraway really meaning not only millimeters, it's about half a meter away. So how could that possibly ever affect the emission of a single trapped ion? Let me just show you. If we just, for example, take the light of a single trapped ion right out, for example, with an objective, with a lens, of course a very good one, take it to a mirror and back reflect it onto the ion, and look downstream at here, at this point in this beam path, then we actually would expect to see interference patterns. And remember, a single trapped ion is a single photon source, because there's just one photon to be emitted and nothing else. So in other words, what we expect to see is that that single photon, of course, interferes with itself at the position of the ion right here, and just creates an interference pattern downstream. And this is what we are trying to observe. And the experiment would look like that. So you just have a mirror that's moving back and forth, and as long as you look at the downstream for the multiplier right this, you would expect to see bright and dark light when this mirror moves back and forth. So let me just show you the result of that. That's something we obtained some time ago. First of all, in the microscope, we just see a single spot of the single ion. The mirror image is there, and once you make the beam path indistinguishable and then move the mirror in the back, you see these nice interference fringes with 72% visibility in those days. We can do this even better. It's just the residual motion that really inhibits further contrast of this visibility. But what do we see here? Think of it as, again, we just can look at the 493 nanometer light in the forward direction where you see the interference path. But this is a 3-level system, and then the back path we can actually look at the red light. If we do that and record these signals simultaneously, then you see the following. There is an increase of the fluorescence in the forward direction and the decrease of the population in the background detection, because there's no interference pattern at the wavelengths of, say, 650. The interference pattern is the same for both colors. But you see that this is, of course, monitoring the population right here. So the population decreases and it increases when you have less fluorescence light here. So we just see clearly that this is enhanced spontaneous emission and this is inhibited spontaneous emission when we just see this as a point. I found this very intriguing because this is a real, very simple interferometer, a single photon, a single atom, and a single mirror. That's the most basic and most fundamental thing I could think of and always intrigued me throughout my life. Let's go on. What else can we do with that? If you have a single atom sitting right there, and let's take about the barium, which is actually an 8-level system, but let's just single out these 3 levels right here. We could possibly, with that imaging capability, we could possibly make also absorption measurements. So the idea would be, in order to see that, replace this mirror with an incoming beam and just see whether we can observe the absorption. This is a bit more complicated just to see these weak signals, and even with the high numerical aperture lens optics here, halo lens, we see a coupling efficiency to the ion of only 0.5%. And if you just go through these things, then of course we can downstream look at the absorption here. We can actually look at the back reflection as well. But let me just concentrate on the absorption part. If you just look at the absorption, then we see that the extinction of a single ion can be measured in the forward direction to about 1.3%. We would have expected from the optics that this is slightly better, but the optics is not quite as good that we could see it. Nevertheless, this is easily observable, and actually we could see even nonlinear effects like EIT resonances and things like that in the forward direction. But we can go ahead and go further using the cavity ideas again that were put forward by Dan. So we just place now a dielectric mirror in that beam path. Remember, this is the probe beam, this is the back reflected beam, and this is the transmitted beam. And here we just replace the atom, or just graphically replace the atom by a mirror, but literally we just have an atom there. If the atom back reflects, as it should, and it did, then we should actually be able to make a cavity which exists just out of the atom and the dielectric mirror right there. And in fact, this is what we do when we just have this high numerical aperture optics, which is then having a, say, reflectivity with that mirror right here. And this is forming a real cavity. How does it behave? Now, this can be done. We see, again, the transmission signal as we have it in the forward direction. Now let's look in the backward direction what kind of a signal we actually see. And if you look at it, then you see this is essentially our mirror and the atom mirror, like a cavity system. You see the transmitted signal, the reflected signal, and the normalized transmission signal. They are completely out of phase. It's a little sad to see that this is just a sinusoidal curve, which really gives you a finesse of 2, so it's not a high finesse cavity that we have. And the reason for that is simply that the solid angle that we collect, that the coupling efficiency that we have to the ion is very small. You would have to have a much higher numerical aperture to get a better coupling. But nevertheless, you see nicely that this can be treated as a cavity. And we went through all of these calculations, and if you just take the ordinary Fabry-Perot calculations, that works in the same way as if you just do a full QED calculations that we actually have done in order to take into account all the changed densities of the modes. So this works with a single atom in free space, and you can actually make a cavity like that. But of course, what we really want to do in the future to make this more efficient, we would have to have a half-sphere mirror. We already have a few of those, and so the half-sphere mirror would really give us a huge solid angle right here, coupling to the ion. And the idea, these are the QED calculations that we've done, that would allow us then to make a real cavity out of a single atom and a mirror. And the hope is that we really can then get also very good coupling efficiency to that single ion. The good coupling efficiency, of course, would lead to an expectation that we get a complete inhibition of spontaneous emission even at a 2 pi solid angle, which now can be used, that kind of a coupling to a single atom in free space, to really couple single photons to an atom. And that's precisely what I told you before. That's what we need in order to make the interface function between, say, a solid, with a stationary qubit and a flying qubit in order to couple information processors. So let me just show you how we go on with that technique to do actually atom-atom entanglement. Instead of having now, say, one atom, we just take two of those atoms. And the basic idea was put forward in this paper by Cabrillo and others from Peter Zoller's group. Take an atom here, take an atom there, and just have a light beam going through both atoms and scatter a single photon here and there, make the beam path indistinguishable at this beam splitter, just record a single photon there. Then, of course, you don't know which one of the atoms scattered the photon, and that really leaves the atoms in an entangled state. Can we actually do this in free space? This Cabrillo scheme would look like that. We have our three-level systems again, so we have two of these Raman transitions. The initializations, of course, would be such that we prepare the atoms both in the ground state. Then, of course, we have to make sure that we have a weak excitation. With a weak excitation, the likelihood of scattering a single photon is, of course, small, but that's what really is important, because we don't have two photons. We just want to have a single photon right here from atom A and atom B. And of course, we get an atom-photon entanglement in each case of the atoms with their internal states and the emitted photon number by the Raman process, which can be written in such a way. So if you just see the atom in the ground state, no photon is going to be scattered. The phase is determined by the laser phase at the position of the atom. Or if you had an excited state, of course, then the atom can scatter, and we see the photon right here. And this can be taken as the basis now to make these things indistinguishable. Say, for example, now this atom A scatters or atom B scatters, and you detect it because you make the beam path now indistinguishable. That means you overlap the corresponding photonic modes with the beam splitter, for example, and project it by detection. And then if you project it by detection, starting from that formula I showed you before, you just can easily show, and that was shown in that paper in 1999, that you can just generate an entangled state of this kind, which really means entangling two atoms across a distance can be achieved by just scattering one single photon of them, no matter how far these atoms are away. The difficulty, of course, that is that the phase is determined by the positions of the atoms and detector, which really means that you need for that, that's the downside, an interferometric setup. There are other experiments where you just scatter, say, two photons and make a coincidence measurements. That goes as the squared of the excitation probability, so it's lower rate, has the advantage that you don't need an interferometric setup. And the other difficulty is, of course, you want to make sure that there's no information left whatsoever which path the photons went. So you must avoid that there's any recoil in the system left. So we want to be deep in the Lamb-Dicker regime for that. And here's the experiment that we actually did. So we took now advantage of the mirror system that we have. We took two atoms and the two ions in the same trap. They're lined up here. There's a few micrometers apart. And so we just now make the following. We just take the mirror, and this is our interferometer that we have. This guarantees that we have interferometric control across all these distances. Then we can make the back reflected signal again, see that again. And the fluorescence of the two ions is made indistinguishable by overlapping these beam paths precisely, as I've shown you before. And we can control the stability with about lambda/10. The rest is just measurement, so you just take a detector right here. Details don't really matter. And if we do that now, we have the following experimental sequence. So we generate the entanglement by just Doppler cooling and have a stabilization of the interferometric phase there of the system. We do optical pumping. We do Raman excitation for 100 nanoseconds. And then we ask ourselves, then we just try to scatter a photon. The question is then, did we actually detect the photon? If we didn't detect the photon, we just start over again. But once we have detected the photon, we know that the system should have been prepared in an entangled state. Then we just proceed to make a state analysis, and in order to do so, we just make a radio frequency transition between the two lower lying states right here, and then we just shelve that state so that we can make state analysis by fluorescence detection and the ordinary shelving. That's a technique that we use with our ions. Now, to make a long story short, when we just generate now that state, then of course the question is, can we actually evaluate the fidelity? And the fidelity can be written in such a way, so we just measure the populations here. These populations can be directly observed from the individual atoms, so we see the ions right there, and we see that in the majority of cases we just have these excitations. Very rarely the system is left in the non-excited states or two excited states, so this is more than 90% right here. And then we have to determine the coherences in order to determine the fidelity. That can be done by a so-called parity experiment, where we just have to vary the phase of the analyzing pulse right here, and from this amplitude we actually see then the fidelities, which come out about 64%, which is not perfect, but it is certainly enough to show you that we are left with some entanglement. And we know that we are limited here mostly by residual ionic motion, so this can be improved by further cooling and by Raman processes that we have when we, by the Raman cooling that we can employ during the measurement process. So let me just summarize this Cabrillo scheme. The Cabrillo scheme is the first demonstration of atom-atom entanglement via single photon detection. So you just need nothing else but having two atoms, say in remote sites. In this case it was just a few micrometers, but in principle nothing prohibits to have these things stay a few kilometers apart. The difficulty is to guarantee the interferometric setup. You just have a single photon detection which heralds the event that you have entangled two atoms. Then the fidelity is limited here mostly by atomic motion, but the improvements are on the way by better cooling and optimized excitation direction, which improves, in our case, the indistinguishability. There's still something left. We have an oblique angle, and there is a certain possibility that we have some information left in the recall. Then the entanglement generation rate just scales with the excitation probability of having a single photon, and this is in our case 8 times 10 to the minus 5. So this is, you can go through all the details, the summary of all these efficiencies, but it needs to be compared with a two-photon scheme where this comes in, the detector probability is squared. And this is the difficulty when you just compare this to the paper by the Monroe group, for example, which is a very nice and wonderful experiment. They have the difficulty that they have about one entanglement event per 8 minutes, which is really not exactly what you want to have, and they need to enhance this using cavities. I'll come back to that in a minute. But here you get things rather for free, because you really just want to make sure that you have a low excitation probability and you get a lot more entanglements, events. So we get 14 entanglement events per minute, so it's about 1 to 2 orders gain simply by using a single photon scheme. That's it. Let me just tell you more about how to scale the system up, and there's a number of things that have been discussed, but the most popular one that we are working on right now is using cavity QED schemes. Of course, the free space coupling is just one exercise, but we also want to do the cavity QED case where we really use cavity in order to fill this photonic channel. Let me just show you how this works. The idea is essentially that we use the ion as the quantum memory. The cavities are supposed to be then the quantum interface for tunable ion photon entanglement, and the force of optical fibers are then our optical channel. The remote ion-ion entanglement has been shown here in a probabilistic way. Using correlation measurements, we could do the same now with the single photon detection, but the question really is, can we do also state mapping, teleportation, and these things? And that's the idea, how we want to use the photonic channel. And for this, we have set up an experiment where we have a cavity, which is about 2 centimeters long, and have an ion trap right in between, and have a single ion just lurking in the center right here. And this mirror is less transparent than this one, so the photon is predominantly scattered along this axis. That's how we have our cavity QEDs from with trapped ions, and we can slide the ions in and out here in the center of the trap. The ion that we use here is similar to the barium ion that I showed you before. It's just calcium in this case, and the qubit transition that we really have at hand is this one between the S1 half and the D5 half transition, which has a lifetime of about 1 second. Now let's see, how do we create entanglement in such a way? Again, it's making use of Raman transitions. If you have the cavity and the ion sitting right there, and then we just make a Raman excitation on the S1 half D state, detuned such a way, so we just create a horizontal polarization on this transition. But of course, we can do this also with a different beam here and create a vertical transition to the other D state right here, the D prime state. And this would generate then immediately an entangled photon where we have entangled the D states right here with the horizontal and vertical polarization of the photons. And this is actually tunable because these two beams are accessible, so we have Raman conditions. We can just set our Rabi frequencies and the phases, so we just can tune this. Let me just show you how this works. When we want to measure this, then we have to map first the state D prime to S by the 729 nanometer radiation. So this is now the entangled state that we're left with. We first map this, then we just measure the state via fluorescence detection. And then, of course, we can do our standard technology. We use quantum state tomography. This is now a routine technology in our laboratory, where we measure the ion undergoing various operations in sigma X, sigma Y, sigma Z, Pauli operators, and in the photon basis, where we have as a basis the horizontal, vertical, diagonal, antidiagonal, and left and right circular polarized basis. And then, of course, we can derive the photon density, atom photon density matrix, and derive everything from that. The result is here. You see the density matrix for such a combined state. This is the real and imaginary part of, actually, I think this is for this point right here, where the phase was set to 0.25 pi. And you just crank through this Raman phase, and then again you can calculate everything that you need. The bottom line saying that we can create entangled atom photon states with a fidelity of 97%. We can evaluate that with the concurrence, or we just can actually see how well this violates Clauser-Horn-Chimney Holt inequality. And so this really shows you that this works with a high reliability and a high fidelity. This is not probabilistic anymore, because we just push the button and the photon gets out, and we know how well we can create such atom photon entanglement. Now, you can actually tune the amplitude by setting these Raman conditions. This is just the atomic conditions that we have. So if we just have here cosine alpha, this is just the parameter that describes the amplitudes right here, then we crank it through, and this the fidelity stays round about at 97%. Likewise, we can do quantum state mapping. So if you really want to map then the state that we give to, say, and a photon state, we do it in the following way. The idea would be that we create, for example, a qubit down in the ground states, S and S prime, and we want to create now a photon which carries the same entanglement in order to convey that information to a next node. We do it the following way. So we just start out with atoms in the ground state right here, prepare that, no photons right here, and then we just map it over that we just are with the atom in the D state and have a vertically and horizontally polarized photon. And we do this in the following way. The state preparation is just done by the usual optical pulses that we have, and then we do the Raman pulses with two detunings again, but starting now from the two states, and we make the detunings in such a way that we indistinguishably go to that D state to carry that out. And of course now you can actually calculate and measure all these things, analyze these things by having various input states, various superpositions, and characterize that again by our usual quantum process tomography. To make a long story short, we evaluate in the end the process matrix, which just characterizes how well you actually can achieve that. So you want this to become the unity process, which just characterizes how well you actually achieve that mapping process. And again, from that we measure that this mapping process can be achieved with about 92%. Which really means cavity QED techniques, either in free space and with cavities, can be used, using your idea of inhibited and spontaneous emission, to really convey information from atoms to photons to bridge large gaps and distances. With that, I'm almost ready. I wanted to summarize here these things. Of course, the question is, where do we go? As I've shown you, we'd like to have a better free space coupling with high numerical aperture devices, mostly mirrors, but there are some lens ideas. We want to use cavity for multi-atom entanglement, and of course we want to do quantum simulations for atoms in those standing waves, in addition to what we do elsewhere, and miniaturize these things and integrate them with our existing quantum computers. This is the team who did the work, and if you want to join it, for those who are here, there's positions available, there are the names. It's not quite the end here. Let me just show you. First of all, I would like to thank you, Dan, for teaching us your deep physical insights and for sharing your passion of atoms and precision with us. I certainly have had a lot of fun reading always your papers, also the Physics Today articles, and I learned a lot. thank you, Bea, for letting him do this and all the support of that. And I cannot resist showing a few pictures. This is the red carpet that the Kleppners always get in Brazil, as you see here. That's actually Randy Hewlett too here. And this is Dan Kleppner, of course, in action. There's even more action. And if you hadn't seen the picture before that Rick Freeman and Philip were telling you, this is the Kleppners in deep appreciation of that. And with that, I would like to say again, happy birthday, Dan, from all of your friends. This picture was actually taken in the very same hotel that we're in these days, about 9 years ago when we're here in Sao Carlos. And this is from all of us in Innsbruck. Happy birthday, and thanks very much.
Couldn't think of a better birthday present than your talk. When I started thinking about these things many, many years ago, I remember trying to address the question of how many atoms you would need to totally absorb a light beam. And I slowly came to the realization that the right number of atoms was 1 if you were in a single mode. And I tried to think of how you could possibly do that and just couldn't visualize it at all. But that elementary principle is sort of sitting down in the basement of what's going on here now. So all I can say is I'm in a marvelous position to appreciate this accomplishment, and I really congratulate you for it.
Thank you. No, I thought you were going to appreciate, because I rarely talk about these things. Most often I have to talk about quantum information processing. But all of these tricks and details, the precision measurements, they are the underlying point that make these things possible. Thank you for your ideas and contributions.
So my question is about any of the experiments where the interferometric distance between the ion and the mirror is important. So for example, in the first thing you described, with the atom, the fluorescence interfering with its own reflection, or the entanglement of two atoms that emit photons onto the beam splitter. You mentioned that in both cases, the fidelity or the contrast was limited by the residual motion of the ions.
Indeed, yes.
So what I want to know is, if you were to reduce the residual motion so that it was gone, so that the atoms were in the ground state, would the 0-point motion contribute anything to the infidelity or the lack of contrast, or is that for free?
I don't think it would, because I have a slightly different view about the 0-point motion as you have. I don't think of it as a real kinetic term. It is really something that is potential term in your harmonic oscillator. And so this is the uncertainty with which you see that wave packet.
Sure.
And I don't think that you can see this as a residual motion that would contribute to that one. We haven't been there. I have not done the calculation. My gut feeling is not.
Okay. Yeah. It's. I'm wondering if anybody else has a gut feeling or has done the calculation.
No, but I think it should not be too difficult to sit down and do this. I'd like to discuss this with you. I had also some questions about your notion
It would
about
be
this.
very appealing, of course.
Absolutely.
If it wasn't true, if it wasn't any effect. I'd certainly like that as the best answer. I just don't know what the answer is.
I don't know, but the reason for that is I thought about this. We can do this afterwards, because you have a single atom there, right there at the field node, and our atom is localized to about 7 nanometers. We know from other measurements that when I just put this at a gradient of the standing wave, because the mirror provides a perfect standing wave there, and I just can put it at the node of that field, but then if it's slightly off the node, then it has a residual motion, and that residual motion, that of course, that leads to an amplitude modulation and also phase modulation of the signal that you can derive with that. We have done some measurements of that. If you're down to 7 nanometers, that is still measurable. So we can really see at the standard quantum limit what that modulation is. And I personally rather think in terms of the uncertainty relation on that. I would not call this a kinetic term, because you can't go any better. But let's talk about this. I think this is an interesting point.